Hey everyone, today I'll be going over Leetcode 49, group anagrams. So we're given an array of strings and we have to group the anagrams together. So we're going to return the answer in any order. So as they said in their own words, an anagram is a word or phrase formed by rearranging the letters of different word or phrase, typically using the original letters exactly once. So all this is saying is, do the words have the same character frequencies, right? If we look at 8, they're anagrams with eat and t. 8 has one A, one T, one E, so do these other words. Nat and tan, same thing. Bat has no other anagram in this list. So really all this means is we need a way to normalize each word. And we need some base truth. We need a key so that every word that is an anagram with another word, they have the same key. So when I say the key, that's like the normalized version of that anagram, right? So let's kind of like go for this logic here, and we're going to actually have a map, and it's going to be a string. Think of this key as the normalized version of every single word. And then each value in this map is going to be a list of strings. So if you look at our result here, and let's actually take this, and let's just put it here for now. And let's call this res, and it's going to be an empty array list. If you look at this, it's a list of strings. So each element in this list is another list, where it's the anagrams, the anagram groupings. So those anagram groupings are going to be stored here in this map. So we have the normalized version and we map it to the list, right? And let's actually just call this map unoriginal, I know, and just make a new hash map. So let's go through these lists of strings, just as normal for each string in strings. Let's actually assume we have some normalization function. And let's just call this a string, normal, equals normalize string. So let's assume we have some helper function, we'll make it later, and we normalize this string. So once we normalized it, what we can actually do, and let's assume this is a key, so all words that are anagrams should have the same normal value. So then what do we have to do? Well, this list might not exist in the map yet, so let's actually make a string, and let's call this bucket because that's the bucket it's supposed to go in, right? Or you could call it list or whatever. And let's do map.get or default, whatever's at this normal key. If it doesn't exist, let's create a new array list. And you do this because, it might not exist yet. And then all we have to do is put this word, mapping it to its normal key. So basically bucket.add string. So we add this string to its bucket. And then we have to also put it back in the map. The reason why we do this is because it might not have existed, so it might be some empty array list, so we actually have to put it back in the map. There's no guarantee it exists in this map already. So that's why we do this. Let's assume it's normal here, and we'll get to this function later. So let's now assume, as I said, this map has list of string as values. Let's assume this map has all the anagram groupings in these lists. So what we would do is we would just go through each bucket, right? And each bucket, and how to get the values in a map, you can actually do map.values here. So this gets all the values in this hash map. So for each bucket, basically, let's add this to result, because this is a grouping. Let's add it, and let's return res. Okay, so this would actually be good. This main function, that should be good. So let's actually create our normalization function. And you might be thinking, how are we going to do this? You'll see it's actually quite simple. So we take some string, we output some string, call it normalize. And basically what we want to do, so what is an anagram, right? An anagram is two words. They're an anagram if they have the same character frequencies. So character frequencies, let's just count the characters. And if you look at the constraints, it only consists of lowercase English letters. So it all ties together, and we can actually just use a character array as the counts. And let's make this a new car, 26 because that's the amount of lowercase English characters. Let's go through each character in string.toCar array. Let's actually count these. You can do C minus A to index it, plus plus to increment it. So all this is doing is just counting the occurrence of each character. And let's normalize it. So let's actually return the string representation of counts. So these are going to be our normalization of each word. And the proof of it is if we look at 8 and eat, these will have the same exact counts array. because they'll have one A, one T, one E, and they'll have the same spots incremented in counts. And we'll return this array as a string. So that'll be our key. So I think we have everything you need here. Let's go ahead and run this, and let's just check. There might be an error. Looks like it's actually pretty good. Let's submit it. Yeah, it looks like it's pretty good. I can live with that. 41%, 45%, and something simple, cut and dry, interview friendly. So yeah, I like this. Let's talk about time and space. Time is actually kind of tricky, depending on how you look at it here. I actually call it OMN, where M is the number of strings and N is the number of characters, right? The reason why is because we have to go through every string, and then to normalize it, we have to go through every single character. So that's why I call it OM times N. It's really clear that way. Some people might call it ON. It's fine. Space is actually OM, where M is the number of strings, right? Because we actually have to fill up every single string in this map. And it's bound to the number of strings because each string is going to be accounted for in this map. No more, no less. So yeah, I hope this was helpful. I really do. Subscribe if you liked it, or whatever if you didn't. Okay, yeah, thank you for watching.